Hello and welcome to your lesson on states of matter. This would be the first lesson in chemistry for the GCSE, going over some basic information you've learned in previous years and taking it a little bit further. So let's go. There are three states of matter: solids, liquids and gases. And you need to understand how the arrangement of the atoms in each of these states applies to the properties that you would see in real life. So I've tried to narrow it down into a core concept, an easy to remember concept that applies and would answer any question that you would get on these three states of matter. So if you look at the core concept, you need to know that in a solid, the particles are very close together, they're actually touching, and they're held in place by strong forces, so they're not able to move around. So they vibrate in place, they do jiggle around, but they don't move from place to place. So if I was to ask you, why does a solid have a fixed shape? You'd look at that core concept and you look at the second part. Well, it's because it's held in place by strong forces. And that would be the answer. If I asked you, why can't a solid be squashed? Again, that core concept was answer the question. The particles are very close together. In fact, they're touching. There's no space for them to get any closer. If I asked you, why does a solid have a fixed volume? Well, again, I would look at the core concept. Which part of that core concept applies to the fixed volume? The particles are held in place. It's not going to get any bigger or any smaller. So why doesn't it flow? Well, again, it's because the particles are held in place by strong forces. And why does it have a high density? So density is about how heavy it is compared to its size, or you might think of it as how many particles in a given space. And the more particles there are, the denser something is. Well, solids have a high density because the particles are close together. Can you see how that core concept applies to every property we would ask you about a solid? So let's consider a liquid. A misconception with liquids is that the particles are no longer touching, they're no longer close together. Now, they're still close, they're almost as close as in a solid, but the big difference is that they are free to move past each other. So they are able to move, but they can't move away from each other. They're still very close together. So let's consider some of the properties of a liquid and see how that core concept applies to the particles. So why can a liquid change shape? If I put it in a beaker, it will take the shape of a beaker. If I put it in a flask, it takes the shape of a flask. Why is that? Well, the reason is these particles are free to move and they flow. And they flow around each other and they can take the shape of the container. So how come a liquid can't be squashed then? Well, again, that core concept is because the particles are very close together. There's no real space for them to get any closer. Why does a liquid have a fixed volume? Well, again, the particles cannot move away from each other. So even though they're moving around each other, they're not able to take up any more space or any less space. They're not able to move away from each other. There isn't enough energy. Why does it flow? Well, the particles are free to move and they roll around each other and they move around each other and they flow. And why does it have a high density? Again, very similar to solid. These particles are close together, so there is a high number of particles in any given space. So finally, let's consider the state of matter of gas. The core concept, the particles are far apart and they're free to move. And the forces between the particles are weak, so they are able to move away from each other as well as closer to each other if needs be. And we tend to find that the more energy they have, the further apart they get. So let's try apply this core concept to some properties we would observe in a gas. So one property of gas is that it can change shape. It can take the shape of a small container, like an aerosol can of your favourite Lynx Africa, or it can take the shape of a room and spread out. So why can it change shape? Well, it's because the particles are free to move and they will flow and spread out into the shape of the container. Why can it be squashed? So this is different to the other two. It can be squashed. And if you look at the diagram, and you look at the core concept, those particles are far apart from each other. And so if I wanted to apply pressure, I could squeeze those particles closer together because they are far apart. I could squash it or compress gas. Why doesn't a gas have a fixed volume? Again, different to the other two. Well, a volume is how much space it takes up. And because these particles are free to move, and because the forces between the particles are weak and they can move away from each other, the gas can fill a larger space or it can fill a smaller space, and it changes volume. So why does a gas flow then? This is a hard concept sometimes. We tend to think of liquids as flowing because we can tend to see them, but gases will also flow. Well, it's because the particles are free to move and move around each other. And gases, why do they have a low density? Well, not many particles in a given space. Well, that's because the particles are far apart. So before we move on, I just want to point out that you often see states of matter indicated on an equation using what we call state symbols. So the little letter in the brackets indicates whether that substance is a solid, a liquid, or a gas. So little s for solid, little l for liquid, little g for gas. The AQ means aqueous, and that means that it's been dissolved in water. Now that will become much more clearer as we go through the GCSE, but it's just a heads up here that we're using those state symbols to find out whether it's a solid, a liquid or gas, and whether we would be able to predict the behaviour from that. So I'm not expecting you to do this progress check. You can if you want, I suppose. But I just wanted to point out that, look, I've included those core concepts, just a couple of sentences for each of those states of matter that I would need to commit to memory. And actually those core concepts can be applied to any of those questions there on the left with relative ease. So it really is going to be about finding and remembering the important concepts that apply to everything else. So hopefully this diagram looks familiar to you. Solid with nice, regular, orderly particles, all of them touching. A liquid, very busy still, very full, almost all of them touching, but a lot less organised, a little bit messy, higgledy-piggledy. And a gas with lots of spaces between the particles to show that low density. Hopefully you would recognise that this first arrow here would be melting. The change of state, the change between the states from a solid to a liquid would be melting. And the change of state between liquid and gas would either be evaporation, that's the one I would normally go for. Sometimes we get away with boiling. I don't really like the word boiling though. And sometimes vaporization. So a vapor is a gas, and that's what that word comes from. It's worth remembering because it sometimes appears in an exam question, and we don't want you to freak out. So what about the other way then? A gas to a liquid would be condensation, and a liquid to a solid would be freezing. The important thing I would like you to remember though is if we are going this direction, we are adding heat energy or thermal energy to change these states. So how does a solid become a liquid? You add heat energy. However, the other way, you are removing that heat energy. You take it away, the particles have less energy, they calm back down, and they go from a gas to a liquid to a solid. So you need to understand what's actually happening when things are changing states. Why does it behave differently? What's actually happening here? Well, if we consider melting, so a solid to a liquid, so we're increasing thermal energy, so the particles that were already vibrating begin to vibrate more. And this allows them to overcome some of the attractive forces that holds those particles together, and it becomes a liquid. So if you look at the little GIF in the corner there, here we go, here we have a solid, and as it gets more energy, they're able to break away. So just adding that energy gives the particles more energy, they're able to overcome some of the attractive forces holding them together. This point here, where you change from a solid to a liquid, is your melting point, and that is different in different substances, and the next lesson will cover that. So what about liquid to gas? Well, it's exactly the same process. We're adding more heat energy, That's causing the particles to move even more, and therefore they are able to overcome even more of the forces, allowing them to then spread out. So the more energy these particles have, the more they are able to overcome this pulling force that holds them together. This point here is your boiling point. Now, what about the other way? The other way, you are removing the energy. So as these particles have got less energy, they can't fight those attractive forces anymore, and the attractive forces then pull them closer together. Now, it's worth noting that the melting point and the boiling point is the tipping point between those states. So melting, it's tipping between solid and liquid, and boiling is tipping between liquids and gases. And therefore, even though we don't tend to call it this, the boiling point is also the condensing point. It's that change. So if I'm heating it up, it's boiling, it's going from liquids to gases. But if I'm cooling it down, it's the temperature where it goes from a gas to a liquid. And that's important when we talk about fractional distillation, when we talk about covalent bonding and ionic bonding. It's worth knowing right now that that is a change of state point in either direction. Likewise, we could say here that the melting point, when a solid becomes a liquid, is also the freezing point if we've taken away the energy. It's when the liquid becomes a solid again. And that temperature, the melting point and the freezing point will be the same for a given substance. So for water, for example, it melts at 0, it also freezes at 0. Okay, before we finish, I just wanted to include just a little bit of knowledge here of the things they could ask you. It has been seen that they've asked how you would measure or investigate temperature change. It's as simple as it sounds, really. A Bunsen burner and a beaker and a thermometer. Just remember that you would need to know the labels of the apparatus. So here, heatproof mat, this is your Bunsen burner, the tripod, the wire gauze, or gauze is fine, your goggles or your safety specs, a stop clock or a timer, your thermometer, otherwise how you're going to measure heat, and this is a beaker, not a flask. Often in a classroom situation, I would ask pupils to heat up ice up until it's boiling and measure the temperature every 20 seconds to see what happens. And the expectation is that the temperature would consistently increase over that time period. But what actually happens is they get a very strange looking graph, and it looks something like this. So you might have seen this already, you might have seen it in physics. It does come up in both. It's called a heating curve, which seems strange given that there's no curves in there, but it is called a heating curve. And if it was going the opposite way, it would be a cooling curve. But the point is, it has these flat areas. So look, there's a flat area there, and look at the temperature at 0 degrees. For a short time, the temperature does not increase, even though we're adding heat. And then again at 100 degrees, for in this case a longer time, we are adding heat energy, but we are not actually increasing the temperature. It stays at 100 for quite some time. So why is that? Well, if I start down here, this is the ice, and we turn on the Bunsen burner and we give this ice some heat energy, some thermal energy. It's getting hotter, and finally we have enough energy to overcome some of those attractive forces. So that energy is breaking those attractions rather than heating up the liquid, or sorry, heating up the solid at this point. And this is the melting. It's now a liquid, it's broken those attractive forces, so the liquid can now heat up. And now we have enough energy to start overcoming even more attractive forces. And so when we are boiling or evaporating, again, there is no increase in temperature because the energy is busy breaking attractive forces rather than heating it up. And that's called the heating curve. In physics, these have got names, and you talk about latent heat, but for chemistry, you just need to know it's there and that you'd expect to see that flat line at the change of state. Finally then, for higher only, you need to know there's limitations to this particle model. It is just a model to help us understand, but it's not perfect. The core concepts, the three things you need to remember, is that the particle model is not three-dimensional, whereas real atoms are. It doesn't show that atoms are of different sizes, and it doesn't show the forces between the atoms. And that's the end of today's lesson.